So the first part of today's lesson, before we actually get into the fundamental theorem of calculus revisited, or the second part of the fundamental theorem of calculus, we're going to look at a few properties of definite integrals, and most of these properties are going to have to do with the limits on the integration. So for example, the first property says if you have an integral that goes from a to b, and another integral that goes from b to c, and you add them together, you essentially went from a to b and then b to c, which took you from a all the way up to c. So if you think of this in a picture, you have some function, there's a, there's b, there's c, and you found these areas. There's the integral from a to b, there's the integral from b to c, and when you add them up, you might as well have gone from a to c directly. Similarly, when you have an integral that goes from b to a, then what happens is that's the opposite or negative of the integral that goes from a to b. So if you switch the order of these limits from b to a instead of from a to b, then that changes the sign of the integral. So from a to b or from b to a, basically when you're working backwards from right to left, it changes the sign of that area or makes it negative. The next one is the integral from a to a. Well, basically, if you go from somewhere to itself, you haven't made any area at all, so the area is going to be 0. So that's where you have this integral from a to a. There's no area at all. And then the last one actually is not about the limits, but about these functions inside. If you are adding or subtracting two different functions inside, this is kind of obvious because we've been doing antiderivatives this way, and you have an integral from a to b, you can do them independently and then add the results. That's basically what that one's saying. So let's do one or two examples of these. So here we go. We want to find the integral we're given the integrals from 2 to 3 of f of x dx is 5, the integral from 3 to 5 of f of x dx is 1, and the integral from 2 to 7 of f of x dx is 11. So we want the integral from 2 to 5. So to get from 2 to 5, we would do the integral from 2 to 3 of f of x dx plus the integral from 3 to 5 of f of x dx, and that would get me all the way from 2 to 5. And then I simply substitute the values that I know. So the first integral was 2 to 3, the integral was 5. From 3 to 5, the integrals are 1, so it's 5 plus 1, which is equal to 6. So there's that answer. Now to get the integral from 3 to 7, what I would do is I would take the integral from 3, from 2 to 7 of f of x dx, and I would subtract, dx, and I would subtract the integral from 2 to 3 of f of x dx. Another way to think about this is to say that I did the integral from 3 to 2 of f of x dx plus the integral from 2 to 7 of f of x dx. It's another way to think about this. And of course, the integral from 3 to 2 of f of x dx is minus the integral from 2 to 3 of f of x dx. So that's the logic I used there. And so when I put the integral from 2 to 7 was 11 minus the integral from 2 to 3, which was 5. So 11 minus 5 is 6. And that's just a coincidence that the two answers are the same. So now we're going to do the fundamental theorem of calculus part 2, which is all about taking the derivative of an integral, a definite integral. So here we're trying to take the derivative of this antiderivative. Now, once you get the hang of this, the procedure is actually relatively straightforward, but you have to be very careful with your notation and with keeping track of appropriate variables. So you can't mix and match variables. If you do, you actually could make mistakes, but also you're stating things that are actually incorrect. So so basically, you can't have more than one variable running around at a given time. Just like when you use substitution, you have to replace all the x's with u's. You can't have x's and u's in the same statement. So if you look at this problem here, you will notice that the derivative we're doing is with respect to the variable x. And the limits in this antiderivative, the limits involve x. Yes, I know there's a constant there, but there's also an x there. But the function inside that integral involves the variable t. It's a different variable here than is here or here for that matter. So these variables have to be the same, and then these variables have to be the same. But these cannot be the same as those. So the idea here is we're going to first work on the inside of the function. So we're going to say let capital F of t be an antiderivative of, let's call it little f of t, which is equal to cosine cubed t. So there's some antiderivative. I don't actually care what it is. In fact, for a cosine cubed t, it would be kind of a pain to calculate. I could, but I'm not going to bother. So, but there is some function. What is going on then is, since capital F of t is the antiderivative of cosine cube of t, we know therefore that capital F prime of t would be cosine cubed t. It's essentially what we're saying. That's saying the same thing in a different way. Okay, so when I now work on just the antiderivative part, of the integral part, the integral from 1 to x of cosine cubed t dt, that's going to be capital F of t, the antiderivative, evaluated between 1 and x. Or in other words, capital F of x minus capital F of 1. So I've calculated now this antiderivative, or this integral. I haven't differentiated yet, but I have calculated this integral, and you'll notice that the integral started with t's. There's still t's here, but once I evaluate it, the variable has now switched to x, and of course there's a constant in there. Okay, so what I'm now interested in is taking the derivative of this. So I say d dx of the integral from 1 to x of cosine cubed t dt is going to be d dx of capital F of x minus capital F of 1. Now here's where it gets easy but also tricky. You have to be very careful. Now, we know that given the variable x right here and here, that the derivative of capital F of x is capital F prime of x. However, this thing here, f of 1, is some number. It's some constant. It is not a function of x anymore. It is some constant. And the derivative of a constant is just 0. So minus 0. That's where it gets a little subtle, because you have already calculated a value, a numerical value for f of 1. So when you differentiate it, you are not taking the derivative of capital F. You're taking the derivative of some number, whatever that number happens to be. So what we've got now is that the derivative of this integral, which is what we're trying to get, is basically equal to capital F prime of x minus 0. Well, we know capital F prime of t was cosine cubed t, so capital F prime of x is simply cosine cubed x. And I'm not going to bother writing the minus 0 part. And there's our answer. So what did I do again? Well, I basically I gave a name to the antiderivative of that inside function, keeping careful care of what variable I'm working with, and then making a statement that, okay, well, its derivative would be the function. Then I anti-differentiated, quote unquote, and got capital F of t from 1 to x, and I evaluated the two endpoints. Then I took the derivative of that and noticed that when it's capital F of x, that's a function of x, and the derivative is capital F prime of x. But when it's capital F of 1, that was a number whose derivative is 0, and that's a very important point. A lot of people make that mistake, that the derivative of capital F of 1 is not capital F prime of 1. Capital F of 1 is already a number whose derivative is 0. So here's another one. Same idea. I want to differentiate this integral, the integral from x squared to 5 of e of t dt. Now, I actually know what the integral of e of t is, but I'm not going to bother. I'm just going to say, I'll change colors just for fun. Let capital F of t be an antiderivative of f of t equals e of t. Although technically I know the integral of e of t is just e of t, and I could do that. But when you get problems like this on the exam, it won't be a function whose integral you know nicely. It'll be something more like this. And the more complicated they can make it, the better, since it actually turns out not to matter in the end. Okay, so the integral then from x squared to 5 of e to the t dt is going to be capital F of t evaluated between x squared and 5. In other words, capital F of 5 minus capital F of x squared. Now I want to take its derivative. So the derivative of the integral of from x squared to 5 of e to the t dt is equal to the derivative with respect to x of capital F of 5 minus capital F of x squared. Now, capital F of 5 is a constant. It's a number. We've integrated f of x, and we've gotten this capital F, and we plugged in 5. It's actually going to be e to the 5, but that doesn't really matter. The derivative is 0. Capital F of x squared, on the other hand, is a chain rule problem. There is a box around x squared. So the derivative is going to be 0 minus capital F prime of box times derivative of box, which is 2x. But of course, box was x squared. But what do we know capital F prime of t or capital F prime of x squared? It's just e to the whatever. So it's negative e to the x squared times 2x, or negative 2x e to the x squared if you want to write it in a more efficient way. All right, one more example. Again, this illustrates a problem whose antiderivative I really would not like to find. It's not that you can't. It actually isn't that bad, but I'm going to try to avoid that. Now, I've written this problem, and the textbook has also done this in a slightly different way. I've already given you this capital F prime and capital F of x, which we have to not use. If they name something, then you can't use that name anymore. Because the antiderivative of 1 over t squared plus 3 is not capital F of x. So we're going to have to call it g or something like that. However, you can see that they're giving you this function, which is an integral, and they're asking you to take its derivative. So first thing I'm going to do is I'm going to say let capital G of t be an antiderivative of lowercase g of t equals 1 over t squared plus 3. Don't really care what function it is. It's just some antiderivative. Therefore, capital G prime of t equals 1 over t squared plus 3. So, capital F of x, which is this integral from x to x squared of 1 over t squared plus 3 dt, is simply capital G of t evaluated from x to x squared, which is capital G of x squared minus capital G of x. Now I'm trying to find the derivative of that, so capital F prime of x is going to be d dx, derivative with respect to x, of this g of x squared minus g of x expression. Now once again, G of x squared is a chain rule problem. G of x technically is 2, but the derivative of x is 1, so I don't really need to call it a chain rule. However, when I take the derivative of g of x squared, I get g prime of box times the derivative of box, which is 2x, minus g prime of x from this part. Okay, so now g prime, of course, we have a function. It's 1 over t squared plus 3. So we have 1 over x squared squared plus 3 times 2x minus 1 over x squared plus 3, which when I simplify is 2x over x to the 4th plus 3 minus 1 over x squared plus 3. And there is the derivative of that integral. So hopefully this procedure kind of makes sense. You just have to, it's very, the procedure is, it's almost identical every time. There's not a whole lot going on. You just have to be careful with the variables. Make sure you use t's for the stuff on the inside. Don't use the same variable here. If they've given you a function name, you got to give it a different name because it's not the same function. And then, when you're doing the derivative part, just be careful of the chain rule. Or if there was a constant here, neither of these were constants, so you could actually differentiate. But it was g of 7. The derivative of g of 7 is 0, because g of 7 is already a number. And that ends our lesson.